And here we go. We have liftoff. Propulsion continues to be nominal.
RCPA chamber pressure looks good.
Probably not. Roger, planet.
Water powers fly! Yes!
Tango down to nominal.
Fighting downside FD off. Bring in FD off. It's orange!
Orange 25! Oh my god! Oh my god!
Decollage. Put that in the big bag, Eagle.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
If there's methane, it'd be igniting in the flare, correct?
Yikes. Keep red. We don't need any more of these.
All right, I'm just going to act like I'm talking to a camera here and hope that the stream has actually started. Somebody tell me, 5x5 in chat, it looks like the numbers are all good. We're going to do this old school mode where it's like somebody in the field who's holding the camera themselves and reading all the statistics and going around and doing the interviews and talking about the rockets and. Jay is in the back channel as well helping us out. But I am going to assume that this is all working correctly because we have made it out to the Spaceport America Cup rocket fair for 2024. It's the first day. We're going to be here all week, but we are in the air conditioning. There's air conditioners up there. I can feel them. We are in the air conditioning for the only day we're going to be in the air conditioning all this week. The NSF team has rolled out to support Spaceport America and ESRA, the Experimental Rocket Sounding Association, ESRA, Accelerator Sounding Rocket Association, we'll say it the other way, for the Spaceport America Cup 2024. I've been coming out here for 6, 7, 8 years now. I'm not even sure how many years I've been doing this, even before I was involved with NSF, but supporting the students who are out here flying these high-powered rockets and making sure that their folks back home can watch what's going on and just sharing all the work that they've done and all the cool stuff that they've come up with is important to me specifically and personally. If you don't know who I am, I'm John Galloway with NSF. You may know me as DAS from other places, but here at the Las Cruces Convention Center, I'm going to be walking around through the field of high-powered rockets here, talking with the teams and interviewing them about their rockets and payloads and trips and where they've come from and all that sort of stuff. So let's flip this around like this. It is literally just me, folks. It's one camera. No presentations happening right now. That's why there's nobody in the seats. But 122 teams have come out here to southern New Mexico to fly these high-powered sport rockets. The rockets go from 10,000 to 30,000 feet and beyond. You can see some of these rockets are 10, 15, 20 feet tall. They use all sorts of different motors. They use all sorts of different technologies. Some of them have payloads. Let's zoom in on a payload there. See the payload? They have all sorts of different things going on. But I'm going to be running around with you just like we used to. Look at this. Look, they're going to take their rocket down. Just like we used to, I'm going to be running around talking to some teams about their rockets, about their payloads, about all the work and science and technology that they put into this. Let me bring up the chat so I can read some chat as well. We're going to do this like Twitch style, IRL style. Only do rockets. This is the only correct way to rate them until they fly. Nice. So let's see here. That's the plan. Any questions before we get started? It is Trey 9. It's a DOS stream. It is a DOS running around the convention center stream. I've got my buddy Art here with me. So how's it going, Art?
Hello.
Yeah, there you go. He has a microphone. He's going to be handing the microphones to the teams and stuff like that. But that is our plan. Grey Wolf says, this is awesome to see. Agent Kerpel said, I didn't know about this. That's so cool. Agent Kerpel, that is literally why we're doing the stream on the main channel. Too many people don't know about this, and people need to know what's going on out here with all these rocketry teams. So, no, BYU, why are you leaving? I was going to go start with that big Alta rocket, but the entire team with the blue shirt just walked away. Art, do you want to go and find us a team to talk to first?
Yeah.
Okay, don't talk into the microphone. Yeah, here. I don't even know if I can do that. Got it. I'm good. I can put it in my pocket. The launch, I'm going to answer some questions for y'all real quick. The launch is actually coming up all the rest of this week. So Wednesday, Thursday, Friday, Saturday, they are going to be launching these high-power rockets out here at Spaceport. But that's the plan. The pointiest rockets are the winners. Jeff, you're right. Anyone trying propulsive landing? I'll ask. I don't know. Does the UK have this? There are teams, James, from all over the world. So it's not just the United States. There are literally teams from all over the world that have traveled from wherever they are all over the world to come and participate at Spaceport. 9-8 Central, thank you so much. We appreciate you. Again, this isn't going to be the hugest stream because we're not doing Starship or anything like that, but this is super important, y'all. So we're able to do this sort of stuff because of y'all's support. Look, very, very college studenty here, right? But it is because of y'all's support that we're able to do this. And let's see if we can't get our first team for some interviews. Are y'all ready to start talking? Sure. All right, here's a microphone for you.
All right, thank you.
There you go.
Okay.
So, real quick, this is the first interview we've done.
All right.
I'm reading chat over here, so if there's questions for you, they may ask you.
Fair enough.
But tell us where you're from.
So we're from Ottawa in Canada. Most of our team flew in. A couple of us drove for 3 days down. We're competing in the 30,000-foot commercial off-the-shelf category, meaning that our motor is a commercial motor. A lot of the rest of the vehicle is developed by students ourselves over the past year. Some projects gone longer than a year, so the whole ground station that's been going on for 2 years, and we have over 50 students from around 13 to 14 departments at our university. So
50 students?
Over 50 students.
So you have 50 students on the team. How many made it down to New Mexico?
About 26.
No kidding.
So the team is pretty interdisciplinary. So we have anywhere between aerospace engineering students to biomedicals that work on the payload.
Yep.
Payload is currently, I believe, in another room getting checked right now. So
nice.
The cool stuff is in here for payload. But everything between airframe, avionics, the parachutes. We have a ring slot parachute this year that was sewn, designed by students. This is a small scale. The full scale is down here. It's a bit of a mess, but...
I said it was very college student. Under the table looks like college students did this.
But
what's going on with these things? What are these?
So these are the bulkheads for recovery. So the vehicle is what's called a dual brake, dual split, dual deploy. So the first split is here. Ignore the joke stickers, the problem, no problem. The first split is here. The second split is near the nose cone. So at apogee, this split happens. Drogue comes out. At 1,500 feet AGL, nose cone split, the main parachute comes out. These guys are the bulkhead responsible for ejecting and separating. So this guy is pointed up, right? And then the second guy sits like that, pointed down. So how these work is a black powder, essentially it's a black powder gun that fires a piston into the CO2 canister, pressurizing the section and popping it. There's shear pin holes. I don't know how close you can see them. There are a few shear pin holes around. They're just plastic nylon or nylon shear pins that go in, hold it so it doesn't drag separate, but once those pop, the whole thing comes loose. I already talked about the drogue. That's the drogue they're flying on.
Yep.
Where's Mateo? Sean, do you want to talk about the ground station?
I want Sean to talk about the ground station.
We got Alex here. Alex,
where's Alex?
Hi, what am I talking about?
You're talking to us about the ground station.
Oh, yeah, this is the ground station. So basically...
Wait, you're Alex, right?
I am Alex,
All
yes.
right, cool. Nice to meet you,
Hello,
Alex.
I'm Alex. So a common issue in the desert is dust and computers. So while most people have laptops with Yagi antennas pointing at their rockets, we wanted to save our personal laptops, and we built this custom ground station over here. So essentially, we have our stack over here, antennas, which talks to the antenna at our ground station over here, which is a custom-made computer, which essentially runs on a Raspberry Pi. And we have our SRAD boards as well, which have our ground station software. Essentially, this all talks to this beautiful screen here where you can see data.
Can I show them the screen?
Of course, of course.
No, like ITAR or anything?
No.
This is reporting telemetry.
Gotcha.
Right now,
so
it's in a conference
this telemetry isn't actually live. If the stack was online, you would see this moving. But essentially, you can see different sensors. We have velocity, acceleration, altitude. And if I were to scroll down, you would see a map. So this helps recovery with our efforts to find the rocket if we want to just see it visually on a map. Obviously, we have redundant featherweights. and other GPS trackers. But yeah, it's our little ground station over here. Do you have any questions?
Very cool. Are those filters?
Yes, they are. Basically to stop the metallic dust particles from entering the case, we have filters. Yeah.
Gotcha.
You
So-
want to talk about QNX now?
We have more people to talk about. So
Yes.
did you build this? A team build this? Like, who came? Is
So-
one team responsible for this?
I assembled the case, but the person behind the design of the actual boards themselves and the stack is Mateo, which is this person here. Mateo,
All
want
right,
to talk
we have
about
another
your
student to talk to.
your stack?
Sure, yes.
Mateo, how's it going?
Good, how are you?
You can hold the microphone.
I can, awesome.
Yeah, you're good. What are you responsible for?
So I primarily work on the software that runs on our SRAD telemetry stack here. So this gets mounted in our fiberglass nose cone and transmits telemetry data about our rocket in real time to the ground station that you just saw Alex talk about.
No kidding.
Yes.
So y'all made, it's not like you went down to the rocket payload store and bought a payload, like you made this.
Absolutely not. Students designed the case. It was made by ProtoCase. Students designed the boards in there. Everything student designed.
No kidding. So are there science experiments on board? Is the experiment whether or not you can talk to the payload? Like, how does that work for y'all?
The payload is a separate experiment. They have a biological payload. This is just the avionics
This is
system.
just the avionics
Yes.
piece. Okay.
Yes.
Gotcha. So the avionics like needs to fly the rocket and separate the rocket at the right time. Like, that's the avionics job.
That's for the altimeter avionics, which are on the bulkheads. This one is more of a, can we get downlink data that we can watch in real time?
Gotcha.
Yes.
So this is like the speed and altitude and trajectory
Exactly,
information.
yes. No flight control goes on in this.
So it's not just like, oh, we got the motor to light and we're done. There's a lot that goes into this.
There is, yeah. We take out all our sensor data and we perform analysis on it. We want to know how much power we consume with our electronics so we can size our batteries for future years. There's a lot that goes into the telemetry data.
Gotcha.
Yes.
All right. So we have, look at all the folks from the team here. I mean, they're like surrounding us, actually. I didn't know y'all were all the way around me. But 360 degrees of the team. What's y'all's team name again?
See you in space.
See You in Space from University
Of Carleton.
From University of Carleton, from Ottawa.
Yep.
No kidding. All right. Are you sponsored by Red Bull or?
No, this is probably just to avoid copyright infringement. The last few years, I mean, we keep it fun. We're a bunch of students. Last few years, we've made named the rocket after food puns.
Yeah.
So we did McNominal 2 years ago.
McNominal.
Yeah, well, it was supposed to be McNorminal. I hope people understand the joke there. But last year was off a Canadian grocery store brand, No Name. It was just a big yellow rocket with no decals on it and just says rocket. And of course, the other side in French. This year, Red Bull. We have a partnership with them.
Red Bullistic, actually.
Yeah, the Red Bull Canada gives us Red Bull, but we don't have a sponsorship.
They give you Red Bull.
Yeah,
All right.
so it's a partnership. So we're not allowed to use their logo.
An important thing. You're not
Yeah.
using their logo, I can
Yeah,
tell.
exactly. It's just masking tape on top. It'll be fine. Yeah.
All right.
Okay.
Well, good deal. We have a ton of teams that we're going to talk
For
to
sure.
here.
Yeah.
Thank you all so much.
Yeah.
We'll see if you can catch you up whenever you're launching. If you see us running around with cameras, come up and tell us how it went or what you're troubleshooting or whatever. But thank you so much for the time.
And be sure to check out payloads and everything else that other teams are working on. A lot of the payloads are being checked right now, so I'm sure it's pretty interesting.
Absolutely.
Yeah. Thank you very much.
Everybody got the not nominal. In the NASASpaceflight chat, in the NSF chat, everybody understood your Innsbrucker reference
we were
there.
gonna put a strut sticker somewhere, but
All right, good deal. Well, I guess I'll get that with my pinky. Folks, we are going to continue walking along and talking with teams, but this is the first of many teams that we have interviewed, and thank y'all. Everybody wave or something, I don't know. Say hi, Mom, or something. All right, appreciate the time, and we'll catch up with y'all later. Good luck. So this is how this goes, folks. We literally talk to one team, and then we walk up. Oh, you need to go find us another team to talk to. We got swag. They give us swag. That's cool. This is literally what we're doing. We're going to go find another team to talk to. Oh, here we go. We can go right over here. Let's just see how many teams we can talk to. Art! Do y'all want to talk? Hand him a microphone. Hold on to this for me. All right. So we're live right now. No takebacks. Okay. You're on the NSF channel, like the mainstream. I don't know how many people are watching right now. No. But tell us a little bit about what school you come from, what your rocket is, et cetera, et cetera.
Well, there's four of us here. We're from Houston Community College. This is our first time here. We're in the 10K COTS, which is commercial off-the-shelf category. So our rocket here is about 6-inch diameter, 10 foot tall.
All right, stand by 1 second. Jay, I cannot hear what Jay is saying, but just stand by. I almost need this in chat because it's so loud here, I can't hear what they're saying in my ears. Chat can just tell me if there's like a problem or something like that. We'll be right back. It was an LOS. All right, let's see if we have the signal. I think we're back. It's just a tough environment, and we have like a team of 2 people. Stand by 1 second. It looks like we're 5x5 again. All right, cool. Yeah, we're good. All right. So I have no clue what they heard, but you came from Houston Community College, the Katy Rocket Club.
Houston Community College, Katy Rocket Club. We've only been here only been a team for about a year. It's the first major event that we've gone to. So keeping everything simple. We're flying to 10,000 feet-ish and hoping to get it back in 3 pieces. If we can do that, we're going to be happy.
Hope you can get it back in 3 pieces.
Yeah, if it comes back in 1 piece, that's real bad.
Yeah. So you said you're not doing anything technical, but you're launching a rocket, so I don't know if I agree with that. You have a mass simulator on board.
Yes. This is a 3D printed box with concrete. We just needed weight, and we didn't have the time or the budget to produce a functional payload, so we came up with the simplest thing we could to hit the required mass for this launch. This is what we came up with, so it's going to stay in the rocket. It's going to hopefully keep us balanced, keep us flying straight and true until we want to pop out our parachutes and come back.
Good deal. So that's a 3D printed box with concrete in it, you said?
Yep.
Just a mass. It's not a mass simulator. It actually is mass.
That's true.
It's not simulating mass.
That's right. Because we're leaving the ground, so it is mass. Yeah.
But that's just fine because you're launching the entire rocket. You have no energetics in the building, but you'll have the motor in it. You'll launch the thing. You have some avionics or control systems here.
We have completely dual redundant avionics that can, give us GPS. They can tell us our telemetry live in flight from 2 separate computers. Both computers can fire their own charges to make sure that we get the parachutes out and get this thing back. Like I said, hopefully in 3 pieces.
You actually have redundant computers.
Of course, yeah. Dissimilar redundancy as well. These are different manufacturers, different batteries. All the wiring's completely separate. There should be no single point of failure in our avionics system.
Nice. And that's actually one of the things they judge you on, right? It's not just, did you fill a box with concrete and launch it?
Yeah.
Things like a dissimilar redundancy, that's an actual engineering thing that you have to worry about in real life. So thinking through problems like that and coming up with solutions is part of the game.
Exactly.
I say game, but whatever.
Competition. Part of the fun.
Cool, good deal. Anything else cool about the rocket you want to tell folks about?
Well, we're going to hit Mach 1 in about 1.5 seconds.
In about what now?
1.5 seconds.
1.5 seconds.
Yep, we're hitting 100 miles an hour in about a quarter second. Our motor will burn out at 1.58 seconds, and that should be just over Mach 1. So if anybody's trying to track this thing, make sure you have your camera, your tripod unlocked, because it's going to be going up in a hurry.
It's going to be like...
Yeah, I don't know what's going to happen after it, after we light it, but it's going to be gone quick. So
good deal. That's the thing with the sport rockets. Like we're like, if you could track a sport rocket, you could track a regular rocket. So, how many people on your team?
Just 4 of us. We got 4 students and we got an advisor.
Are 3 of you here? 1, 2, 3.
We got 2 students and we got our advisor here.
Okay. I thought you were the student. All right, cool. The advisor. All right. Yep. So you have a team of 4 people.
A team of 4 people.
We just talked to a team that had 50 people.
We're newer. We're making it work.
Well, that's awesome. Look. You have a rocket on the table.
Yep. We're all on propulsion. We're all on avionics. We're all on recovery. We're all on structures. We're all part of every team, and we're, making it work for what we got. So
very cross-functional. How many G's during the launch?
29.8, I believe.
9.8?
29.8.
29.8.
Yeah, it's going to be moving.
It probably says on the thing there somewhere.
29.7.
It actually does say 29.7 G's right there.
Yep. So
no kidding.
That can break things. Hopefully we built it sturdy enough that won't happen, but we're going to light the motor and fingers crossed it comes back safe.
Good deal. Have any of y'all done this before?
Never. We've launched rockets, but not this big.
You've launched rockets, but not this big. Y'all are going for 10K.
10K, that's
10K. Actually, it says on your name badge, 10K COTS, 10K commercial off the show.
Yep.
All right. Well, good deal. Chat says this is very impressive for 4 people.
Thank you.
Very impressive. Small but mighty teams. 29.8 people are wondering how is that possible? Mass versus thrust. It's the thrust to weight.
Yeah. Oh, thrust to weight. What do we have on here? Yeah. People-wise, we definitely have a high thrust to weight with like 4 people per team. But
good grief. All right, folks. Well, we're going to continue walking around and talking to other people. Thank you so much. If you see us out in the field, good luck with your launch. We'll try to track it if we can keep up with 29.7 Gs.
Well, good luck and thanks.
All right. If you see us out streaming, come tell us how it went.
Will do.
All right.
Awesome.
Take it easy.
I'll too.
Thank you. Folks, we are going to keep, this is literally how it is. We're going to keep walking around. We'll see if Art has another customer. Art has gotten us another customer. Who is this? GW, George Washington University.
Yes, sir.
Who is talking to the NASA spaceflight crew?
I will be.
Here's a microphone.
Oh, sweet. And then we'll be talking for a little bit.
Okay, just pass the microphone when you're ready.
Sweet. Okay.
What school are you from? What are you flying? Tell us about it. We're live.
Sure. Okay. Hello. So we're George Washington University. We're from Washington, D.C. We're team number 39, and we are flying Cerberus. Cerberus is a dual-stage rocket. It's 22.5 feet long. I think it's the longest rocket here in the convention center.
Wait. This isn't the rocket?
Oh, that's not. That's half the rocket.
That's half the rocket.
The other half is right here. Yeah, so we're stacking this thing. We have 2 motors. One is our booster motor right here. It is 115 millimeters. This is the retaining ring for that motor.
Okay.
So it's a very, very large motor. This motor has a full Finnisil grain geometry. So it's that star pattern. That means that we are burning very, very fast and very hard. 2,000 pounds of thrust out of the pad.
It's a lot of surface area inside the motor.
Exactly.
2,000 pounds of thrust?
2,000 pounds.
For the first stage?
For the first stage.
Yep. Okay.
So that's 13 Gs that we're accelerating at.
I mean, they have 29 Gs, so I don't know. You shouldn't have set up next to them.
Yeah,
I'm kidding. Go ahead. Theirs isn't 30 feet long. So.
Theirs isn't 30 feet long, so we've got that going for us. Okay, so we come off the pad, 129 feet per second. That burn happens for 2.5 seconds.
2.5 seconds?
2.5 seconds.
Just
Yep. At the end of that, we're already at 2,100 feet. And that's when we separate stages. So 1 second after that, our sustainer gets kicked off with 1 gram of black powder.
This is the second stage?
This is the second half of the rocket.
This whole thing?
Yes.
I gotta back up. Hang on.
Yeah.
You can keep talking.
Okay.
So this is the second stage?
Yes. And for reference, I'm 6 feet tall, 6'3". And this is 12 feet. So this gets kicked off, and it has its own motor. Now, it's a much smaller motor, an L750, and it has this grain shape here. So it's a inch diameter internal grain, and it's only a 98 millimeter motor. So a bit smaller than our booster.
Gotcha.
Okay? This one burns for 5 seconds. Takes us up to about 10,700 feet.
So you're going 2 stages to 10,000 feet?
Yes.
Why?
We are crazy. No.
We're crazy.
No, so out in the desert, when you're recovering a rocket that goes 30,000 feet, odds are you lose it in the clouds or you lose it, 10 miles away.
Yep, and then you end up on a walkabout trying to find it like 10 miles down
Exactly. Or somebody tells you it's here 4 months later and you can't come out. So our goal is to be able to recover the rocket, but also make something that's, interesting and lets the team grow, in terms of complexity.
Nice.
Yeah. But on top of that, so it's not just a 2-stage rocket.
But wait, there's more.
There's more. It's a 2-payload rocket.
It's a 2-payload rocket?
Yes, sir. So we have 2 deployed payloads. First is our quadruped. Now this right here is a dummy quadruped. This is the actual quadruped, and it could not make it with us here today for competition.
Ah, okay.
Okay, so we have the dummy.
Is it here, but this is just a dummy for today, or is it?
It's not here for Spaceport.
It's not flying. Okay.
Yeah, not flying this year. Maybe next year. Yes. So this dummy payload is deployed at 1,500 feet from the booster section. Okay, so that's the first section here.
It's a booster payload?
It's a booster payload. Now our primary payload, the one we're
crazy.
Oh,
all of you. You're all crazy.
Yes. Oh, there's more after this. Trust me. So this is our primary payload. It's a search and rescue optical navigator.
Okay.
Now for Lord of the Rings fans, Sauron, and we have the Eye of Sauron right here. There's a small camera pointed at the ground. Yes.
It's less impressive than in the movies, but
a little less impressive. But trust me, it's worth it. So this gets deployed from the sustainer right under the nose cone up there at 1,500 feet as well. Now, as it comes down, we have a reaction wheel right here.
There's a reaction wheel.
A reaction wheel. And this spins up and keeps the payload from spinning as we come down. Now, the payload has a GPS system, okay, that tells us where the payload is and gives us an approximate altitude. It also has a barometer for secondary altitude check.
Okay.
It has a magnetometer for orientation.
How's it do the primary altitude?
Primary altitude would be GPS.
GPS?
Yep.
Okay,
Yep.
And the secondary is barometer, it measures the pressure, and yeah.
Exactly.
Gotcha.
And then we have magnetometer for orientation, IMU suite for secondary orientation.
Okay.
And then we have that ground-facing camera. We did a camera angle to pixel calibration.
Right.
Okay. So if we identify an object and we can click that pixel, then we know what angle it is relative to the payload.
Relative to the payload.
And we know the altitude of the launch site. So we can, using fancy math, determine the coordinates of the things we identify.
No kidding.
We have TensorFlow object detection. So it's a neural network.
Yep.
It is identifying 5 things. Roads, groups of shrubs, cars,
groups of shrubs.
Because you can use rockets and shrubs.
Yeah. Nice.
They have
a shrubbery detector on board.
We have a shrubbery detector. Yes. The folks over at Monty Python, they'd be proud.
There you go.
Yes. And then we can also identify buildings, and then most importantly, other people's rockets, including our own.
Really?
Yes.
So I was going to say no kidding, but I stopped myself.
No, so you hear horror stories, right, about how many teams lose tracking and lose their rockets when out in the desert, and sometimes you need somebody to look for it. So search and rescue. That's what this is for. Yes. So we have that all transmitted because sometimes your payload doesn't come back. It's transmitted live to a ground station.
Yep.
So we can do secondary processing on the data, and we can point out, hey, somebody has a rocket here, even if we don't detect it.
No, I'm going to say no kidding.
Oh, please do.
You burned a no kidding.
Okay.
How many people are on your team that have done all of these different things?
Okay, so I'll be honest. In the past, we've been a pretty small team, 10 people. Recently, we were able to bring 14 people with us. One of them could not make it.
Okay.
We have about 20 active members right now.
20 active members.
And that's been a big step for the team.
No kidding. And you've got how many here?
We've got 14 here.
14 here.
Yeah.
That have come all the way from Washington, D.C.
Yes, sir.
Look, I have to read the sign, all right? I go and I'm like, oh, they're in Washington, D.C. And then I'm like, you came all the way from Washington, D.C. Movie magic.
Yes.
Anyways.
So, one more crazy thing.
But wait, there's more.
But wait, there's more. So, I'm going to hand this off over to Leo. I just want to say our booster actually has a podium presentation because we're doing something no other team is doing.
Okay.
2 things one combined no other team has been doing or has ever done. Okay? We are taking live data of our rocket as it performs. So I'm going to hand this over to Leo, and he's going to tell you guys a bit more about that.
Okay, Leon's going to tell us about the live data.
Thank you. So what we're going to be doing here for the first time is we want to understand, you might do as much ground testing as you want, but it might not represent how the engine actually performs in the air. So what we're doing is we're doing a full 3-dimensional analysis of the thermal data of how the engine is performing in flight, and then also inside we have a pressure transducer to be able to see how the pressure is changing throughout the engine as well. So we can get a better idea of how the engine actually performs when it's flying in comparison of when you do your tests on the ground.
No kidding.
And then on top of that, what we have inside of here, let's say you put your whole thing together and you can plug your sensors in each of these holes, right? So you can easily replace them if they're broken. But
that's what the harness is.
Yeah, these so these are wires. We run the cabling on the outside of the rocket.
That's like your raceway, basically.
Exactly. And then we put the thermistors inside there, and they rest against the casing of the engine.
Yep.
And then you have your board inside. Everything's assembled. You can't access your board. How do you know that your stuff is still working? So we were thinking, similar to like a USB drive, you can plug that into a computer or something. We have a system where we can just plug a cable into our rocket and then bring that to a console board, and that will display exactly which systems are operational or might need to be replaced.
Like it checks out the whole rocket, almost like
exactly.
an automated go, no go or something.
Of course, and then you can replace it before you go to the launch pad if needed. So, yeah.
Folks, look, I've talked about how important it is, the work that the students here do. You don't know how cool this stuff is, but that is why we're here sharing it with them.
Thank you.
All right. Folks, tell us anything else we missed. We have so many teams to talk to.
I'll tell you what, there are a lot of great people out here.
Yep.
A lot of good competition. Every year we've been doing this for the past 10 years.
10 years.
Before they were doing Spaceport. Yeah. And I'll tell you, the past 3 years since COVID hit, it's just been excellent. So you're going to see a lot of cool projects. Maybe none as tall as ours or as
wacky,
crazy and
stuffed full of features.
But that's kind of what we're here for. And I wish you luck.
All right, good deal. Will y'all wave to the camera here as I don't run into your rocket? There we go. It's Team 39 from George Washington University. Y'all, thank you so much for the time. We're going to keep on talking.
Appreciate it.
Yeah. So cool. Catch up with us in the field and tell us how it went.
Definitely. Thank you.
All right. And now we just keep walking on to the next. Where'd my guy go? There's Art. Let's go find another victim, chat. Who wants to talk next?
There.
Oh, what color?
The white rocket.
The tall gray. All right.
All the gray shirts.
Let's go talk to some more people. Let him get a picture here. Look, rockets.
They weren't here when I did my read.
Gotcha. Oh, excuse us. All right, y'all. I warned you. This was coming. Who wants the microphone?
I'll take the microphone.
There's a microphone.
All right, sweet. All right.
All right, let's make sure we're all good here. We've moved around. What team number are you?
We are, team number 20. We're Clarkson University.
No.
Shut down.
Team number 20. Where'd you come from?
Clarkson University. So that's Potsdam, New York, way upstate New York. So over the past few days, we did 3 13-hour days of driving to get down here.
3?
Yeah. It was not pretty. It was not pretty. We all wanted to kill each other by the end of the car ride. But it was like Airbnb to Airbnb. But yeah, definitely.
So you drove all the way out here, and your rocket made it. It's got a tennis ball on top.
Yeah, no, it's a remove before flight tennis ball. It's very important.
Remove before flight tennis ball.
We've destroyed so many ceilings at our university. Like we have to do it. Like my dorm room's a mess.
Does it just stab into the ceiling material and rips it up?
It's it's a foot longer than you remember it is, and all of a sudden there's a hole, and you're pulling it out of the drywall. It's, the usual story. But
all right, so tell us about your rocket. You're going for 10K?
Yeah, so we are a 10K COTS team. This is our first year at Spaceport America, actually. So I founded the team with some of these other people here 2 years ago. Last year we went to the Battle of the Rockets, which is a smaller competition in Virginia. And then this year we were able to get into the Spaceport America Cup. So this is our rocket Carrera. So I don't know if anyone is familiar with the Porsche 911 Carrera, but we have some very big car nerds on our team. And they hijacked the voting process for figuring out what the name is. And since we're Clarkson University Rocketry, we named it Carrera. So a little bit of a pun there, but we got the beautiful Porsche lettering on there.
I feel like I gotta do it like this so they can get the lettering there.
Yeah.
Carrera.
And we even butchered a Porsche logo on top. That says,
I show that, or are we gonna get like DMCA?
Yeah. YouTube strike right there. So we had a lovely team like during senior week, just in the pay booth painting instead of going to the bar crawl, all that sort of stuff. But
how many people do you have on your team?
So our team is like around 20 to 25 people. Typically, it'll start out about like 40-ish at the start of the year.
Okay.
And then people realize they need to pass their classes, then it whittles down a little bit. Yeah, so I guess a little bit more about like the actual technical details on our rocket.
Sure.
We're flying in an Aerotech M2500.
That's just the casing, right?
Yes, this is just
no energetics in the building.
Yes, no.
I read the signs on the way.
Yeah, we get chased out with pitchforks if we brought that in.
As long as there's no torches.
Yeah, I know. Yeah, exactly. But then we've also got payload this year. So we're a team with a functional payload. What we're doing is we have like a black box flight recorder. So right here, it's pretty heavy, but what it is we have a bunch of electronics inside there, like an IMU, we have a pressure sensor, we have a load cell, and what we're doing is we are gathering a whole bunch of data that we hope that if we have some sort of flight anomaly, we can recover those electronics in a state where maybe the rest of the rocket isn't recoverable, but we can get those electronics back, specifically with the little SD cards in there, and we can actually do a more in-depth analysis on what actually happened. So we have like a pressure sensor that goes in this parachute bay, and we can tell if did these charges actually fire when we were wanting them to, and did they fire and maybe it didn't separate, or maybe we see live telemetry from our flight computer saying it did, turn the pyro channels on, but maybe it just didn't actually ignite them. We can get a lot more insight into any sort of like mishap investigation that we have to do after.
Investigation,
exactly.
nice.
I've been watching too much NSF. I'm using the terminology now.
Too much NSF, nice.
No such thing, right? Yeah. But then,
I like this. This is good. Keep it up.
Yeah, definitely. And then we've also got an active air brake system.
Yep.
So what this does?
Active air brake system.
Yeah.
That's what this is.
Here,
I'm pointing the camera at it.
Yeah, exactly. So what it is we have a servo motor and a whole bunch of custom fancy electronics in here. This is just a 3D printed model.
Yep.
And that servo motor, based off of commands from our custom flight computer we made, tells these flaps to either deploy or retract to target our 10K above ground level altitude that we want for our apogee.
So you literally look at your speed and energy, I guess, and altitude, and if you're going to overshoot it, you deploy the flaps.
Yeah.
I feel like those need a special name.
Yeah.
Flaps. Do you have a special name for them?
I think blades sounds cool. It sounds very metal, very hardcore.
So if you're going to overshoot it, you deploy them more to get more drag so that you get closer to 10K. And if you're going to undershoot it, you suck them all the way in so that you get as close to it as you can.
Yeah,
because that's part of it. Let me make sure I don't run into anybody.
Yeah.
You're not just we're going to launch a rocket. You're trying to get as close to 10,000 as you can.
Yeah. So one of the big things with this competition is we're scored on our technical reports, our quality of construction, all that. But at the end of the day, a very, very large portion of our score is they plug how far off we were from the target apogee into an equation, and then it pops out that little bit of our points, and that can very much make or break a good competition year if you're like 1,000 feet off, or if you're 2 feet off. That's a very, very major difference.
And that's actually a question people don't understand. Why would you want to go lower? But that's because they're shooting for that target altitude. It's not just launch a rocket and see how high it goes. It's launch a rocket and see how close to the target altitude you can get it.
Exactly.
So it's almost like you don't even want to go over. If you could stop it right at 10K, that's what you want to do, and that's why you have that thing.
Yeah, precisely. Yeah, so that's a 3D printed model, a little bit, some fit checks and all that.
The actual one is here.
So I think I'm gonna see real quickly if I can actually. We have a test script on this, and it should flex them in and out. I'm gonna see if I can get it to work. It's sometimes a little finicky, but sorry. Yeah. So what we. Yeah, look at that. So very, very beautiful.
Press a hold down to reset button, or there's a little switch or something in there?
So we got a rotary switch in there that all the way to one side to power off, all the way to the other side to power on.
Okay.
And then it just boots up and runs this little demonstration script. So
it's just going to go on and off until you stop it, or does it take times? Or?
Yeah. So this does it infinitely. So when we this is just like a little demonstration one that we have.
Yeah.
But when we actually go to fly for our actual competition flight, what we do is we upload a different code to that. That's our flight code. And what it does is it starts up. It does a bunch of system checks, so it checks that each of the individual sensors are connected. So we have onboard data login. So essentially, we have a half a gig of flash chip storage on there, and so that's logging all of the different sensor readings that it takes throughout the time. So not only are we monitoring altitudes and accelerations and everything, but we're also able to measure temperature and pressure and all these other things.
A whole suite of sensors.
Yeah, a whole suite of sensors, and it's really neat because we are the IMU and the barometric altimeter, they have little temperature sensors in them, so that behind the scenes they have these little corrections that they make for temperature.
Right.
But we can also just directly take that temperature reading from the sensor as well, and then we don't have to worry about that, and we can get some really interesting data on if we're sitting on the pad on a 105-degree day for an hour and a half. We've done some back of the napkin heat transfer math, but we really don't know what it's going to be like until we actually go. So we can get a whole bunch of really, really interesting data just by logging every single tidbit of information.
Thing that comes in.
Everything.
Log it all sorted out later, basically.
Exactly. Yeah.
Nice.
100%.
All right. Anything else interesting about the rocket? It's just continuing to do this.
I like shiny things. I like things that move. It's very nice. Yeah.
All right.
Yeah.
Well, we will catch you out around the launch sites.
Definitely.
If you see us walking around, interviewing or talking to people or whatever, like come up and tell us how it went or what's going on.
Yeah. Hopefully, no tears in my eyes tomorrow.
There'll be tears in your eyes. It's dusty out there.
Yeah, exactly. Tears of joy. Tears of joy.
Sweat in your eyes. So.
Exactly.
All right. Well, folks, this is Team 20. And we will catch up with you all on the launch pad.
Thanks so much.
I was going to read. I was like, it's Clarkson University, and the rocket was in the way. I'm like, I can't see.
Yeah, the rocket's too big. It's no such thing.
All right. Well, good luck with y'all's launch. Pinky me the mic there.
All right. Have a good one.
And we will see you later. We're just handing it this way next. Thanks, y'all.
Slide here.
They took their rocket together especially for us.
Let me make sure we're all still good. Chat, tell us if we're still good here. They have assembled. What are y'all doing? The rocket here for us. Who are y'all with? Embry-Riddle.
Embry-Riddle, Daytona Beach.
Embry-Riddle. We know some people that went to Embry-Riddle, Daytona Beach.
Yeah.
We have some folks that do commentary and stuff.
I know exactly who you're talking about.
You know exactly who we're talking about.
Yes,
Excellent.
I do.
You can tell them hi if you want.
Hi.
Okay, cool. So I'm going to go this way.
Yeah. Whatever works.
I have to back up because this is ridiculous. What are you?
It's 20 and a half feet.
20 and a half feet.
Yes, sir.
All right. So, are y'all going to hold that for like 10 minutes or what?
We can. Hung it for like an hour yesterday, so we'll be all right.
All right. Tell us about this contraption that you've put together, and what were you thinking?
Well, so this is Artemis Mark V, 5th iteration of the project. The project's been around since about 2009 and competing in Spaceport and IREC since 2011.
Okay.
We've got big motors, a lot of avionics bays, so kind of needed room, and in gross oversimplification, but to an extent, longer yard, a little more stable, to the point where we're actually a little overstable.
A little overstable.
Yep, we have a stability of 2 caliber off rail and 6 at separation.
No kidding.
So, more
does anybody know what that means? I actually don't know what that means. What's that mean? I'm like, it sounds like a lot.
Caliber's pretty much just your diameter. It's just a measure of stability.
Ah, gotcha. So. And is that how much it'll deviate from the diameter of the rocket or something?
I believe so. Yes.
Okay. Cool.
Yeah.
Gotcha. It's overstable. Nice.
Yes.
So payloads, y'all don't have to hold that together. How are you going to get it down?
Same way we got it up.
How? What? All right, we might have to film that part.
We can.
What sort of payloads do you have on board?
So
it looks like 2 stages because it's got 2 sets of fins.
Yeah,
I worked that out myself.
Yeah. So our payload is it's a gravity acceleration crush test. We have 2 steel pipes, and so ideally it's to see if the acceleration of the rocket is enough to deal enough force onto it to get it to go past its yielding stress and back.
Gotcha. Did you just say do a force onto it?
Did I?
I
probably did. Whatever.
I'll allow
I'm trying to put stuff into words. Oh well.
We got the thumbs up. So what's the force at liftoff? The thrust to weight? Like, give us some numbers about it.
Thrust to weight is it's 12 to 1 off pad.
Okay.
Off the top of my head, our max acceleration, I want to say around 8. I want to say like 8.6 Gs.
Okay.
And our max velocity is Mach 1.5.
Mach 1.5.
Before separation, it goes about Mach 0.8 just before transonic.
Gotcha. And y'all are going for 30,000 feet, right?
Yes, sir. Yep.
30,000 feet. So it's just it's going to make my arm hurt pointing up at the top of this rocket. It's the second stage that's supposed to go all the way to 20,000 feet. Is it taking a payload up there or what?
Yeah, it's taking the payload up. Payload bay is in the sustainer. If you see that, I don't want to make you point it up anymore.
I got it. I'm good.
That lower gold ring is where our payload bay is.
The second gold ring?
The lower one.
The lower one. Okay.
Top one is our avionics bay.
Top one is avionics. The second one is payload. All right. Good deal. How many people are on your team?
Here with us, we've got 7 people, but our team is about 20.
About 20 people.
Yep.
And did y'all drive? I mean, you had to transport the rocket, right? You don't put in your checked baggage.
Yeah, two-day drive from Daytona.
2-day drive from Daytona.
Yeah.
No kidding. All right, I feel like y'all need to let that thing down. Like, can we watch you try to destack that thing?
Sure. Yep. There.
What if? Yeah. What if you had a tall tower that had these two chopstick arms on it? Would that be? No, I'm kidding. Let me back up so they can do this here. They're going to catch the rocket. I got to back way up.
You can keep coming back if you need.
They're going up again. We're getting a picture apparently. Oh, they're going to take a pic. Okay, we're taking a picture first. Up the rocket. Great.
They put that together especially for us.
We do need CP11. Well, I feel like we should get in on this action. Hang on a second. If they get to do this, why can't we do it too? Look. There you go. Look, all the way up the rocket like that. There we go. Okay, cool. Now we're going to back up again. Make sure I don't back into anybody. Everybody. Have we got to the... Okay, we are on the second stage here. Yep. There you go. This is ridiculous, y'all. Oh, it came apart. Yep. It's supposed to do that. All right. Well, we took the microphone. We are going to move on and continue interviewing other teams.
Let me go give them a
Y'all have good luck with your launch, and if you see us out there, let us know how it went.
Yeah, thank you very much.
All right. Thanks, y'all.
Thank you so much. I love watching your launches on YouTube, by the way.
Wait, say that to the microphone.
I love watching your live streams on YouTube of all the NASA launches, the SpaceX stuff, everything.
Nice. I like it. A ringing endorsement. Yep. Thank you all.
Are you from NASASpaceflight?
I am from NASASpaceflight.
Nice. I love watching you guys.
Thank you. All right, where did Art got us another set of folks to talk to here. So we're going to keep going. Let's see who we're talking to next, y'all. Oh, look, a payload. Do we have someone else to talk to? Have a microphone.
Thank you.
All right, what's your team number?
So we're Team 16, Case Western Reserve.
Case Western Reserve. All right, what do you got here on the table?
So currently here we have our lower body tube and our fin can. This is our first year doing totally SRAD composites, and this fin can was made with a 3D printed mandrel, and then we had tacked on fins, and we did a layup with CF there.
All right, tell us real quick, SRAD.
Student Research and Design.
Student Research and Design. Okay,
yeah.
So you didn't go to the fin store and buy this.
Absolutely
like students
not.
research and designed this.
Right. So we yes, exactly. So we bought the carbon fiber sheets, we bought the fiberglass cores, and the carbon fiber sleeve, and then we used our 3D printer and designed the mold to go on the inside, dealt with all the tolerances to make sure that we could shrink the mold enough so that the fin can would be the right size, and we did all the layups and composites ourselves.
No kidding.
Yeah.
So is it just the fin section that's carbon fiber like that, or is it the entire...
the entire thing is carbon fiber, and this was our first year doing carbon fiber tubes as well. And
can I do this? Can I look in here?
Yeah, go for it.
Hey.
Yeah, so you can see all the way to the other end. But what you can imagine is, since this is a tapered section, it's smaller on one side than on the other, so it's really easy to be able to push the mold out, whereas these are straight all the way down. And so we actually took a piece of aluminum tube and turned it down really, really accurately on the lathe to make sure that it would be able to pull these tubes off. And this is our first year doing it, and so we actually made this in tube. It looks really good with the paint job now, but it's two separate tubes with a coupler inside that we epoxied on. And so it was a whole bunch of experimentation, and we're really glad that we made it here in one piece.
Have y'all done this before?
So we have done stuff. Last year we made a bow tail in the similar way that we did this year. We've done fin cans before, but this was our first year doing tubes and the nose cone as well.
Gotcha.
Yeah.
So what is this part? It looks interesting.
Sure. So this is our air brakes mechanism. It's been in development a few years. Sadly, this year we weren't able to totally complete the process, but what we have here is a DC motor that drives this plate up and down. That drives these linkages, and I'll actually turn you to our poster over here, where were everything to go well, we would have these flaps that would come out and actuate in order to make sure that we can hit our desired apogee as closely as possible.
Gotcha. So this system right now isn't fully functional, but this is like the basis of a system that would have those flaps added to it.
Right, and we were a little ambitious this year. We took on a lot.
That's good.
And so the mechanism is actually really helpful to keep our weight and stability all all nice and good.
Good deal. All right. Yeah. Y'all going for 30K, actually?
For 30K this year, yeah. So this is our second year competing in 30K. Yeah, we're excited.
All right. Where's the pointy bit?
Oh, so we took that home. We have some work to do on it. So sadly, the nose cone is currently in the shop.
I feel like the rocket needed a pointy bit. So
yeah, it typically does.
All right. How far did y'all have to come? Where is Cleveland, Ohio?
Yeah, so that's around 30 hours of driving. We had a few different team members make the ride down. Garrett over there is our wonderful star driver.
There's Garrett. Nice.
Yeah, he has the big car, and with the big car comes big responsibilities. So we're really grateful that he drove down and brought most of our things.
All right, good deal. Awesome. Well, if you see us out there, tell us how your launch went. Tell us what's going on.
Awesome, yeah.
We appreciate you letting us know about the rocket, and good luck with your launch.
Thank you. I'll give this back to you.
Just like Pinky it there, and we'll move right along. Here's one last look at the rocket. That was Team 16 at Case Western Reserve. All right, thanks, y'all. Okay, we're going to find Art, and we're going to go talk to another team. It's another rocket. Who am I handing this microphone to? There you go. All right, what's your team number?
So our team number is 43.
Okay.
And we are Team Abhiday from IIT Madras. So this is a Chetak 2.0, and we have developed this rocket as an inspiration from our previous year launch.
Yep.
So last year was the first launch that we had. That was Chetak 1, and we realized like there's a great scope of improvement. So this year we have implemented a lot of new things. Every vertical has done great work. So as you can see, one of the most significant improvement that we have done is the canard system.
Yeah.
So in order to reduce the roll that is there in the flight,
right,
we implemented a canard system. So how it works is basically after a certain point in altitude, the canards will detect the roll and limit it to a very limited value,
right,
so that the rocket doesn't spin too much.
So they're actively driven, right?
Yeah.
Like they're
actively.
actually controlled. You can see that they can turn, and you're going to be using that to try and control the spin rate of the rocket.
Yes.
Excellent. Okay.
Another thing that we have tried is basically having a reefing mechanism. So this year we are going with only single parachute, and we'll be using it as both drogue and main parachute.
So just instead of a smaller drogue and a main, you just have a single parachute.
Exactly.
Okay.
And another thing that we have tried is a minimum diameter. So our payload is 16 centimeter, but the casing is 98 millimeter.
Ah, yes. So you can see it actually looks like it has a payload fairing that's a wider diameter than the rest of the body of the rocket.
So we went with this transition basically in order to reduce on our weight, and this has proven a great implementation of our design. And we also this year have one SRAD system in avionics.
Right.
So we are going with 2 COTS and 1 SRAD. So this is a new thing that we are trying.
So just to tell the people watching, you said one is COTS and one is SRAD. COTS, folks, means that it's commercial off the shelf, like they buy the avionics system. SRAD means the students designed it, like you researched and developed it yourself. So you have 2 avionics systems, one you purchased and one you built, right?
Yes, sir.
Good deal.
Thank you.
Thank you. We have some very well painted fins as well.
So very well painted fins. I feel like you were in charge of painting the fins.
No, I'm the team head. I look over.
Okay, all right.
He's the teammate.
Okay, so y'all came here from all the way. How far? How long did it take you to get here?
All across the Atlantic. 2-3 days it took basically.
3 days?
Yeah.
How do you get the rocket here? Did you ship it or?
Yes.
We shipped it through the flight.
Yeah.
DHL helped us. So yeah. And this is our payload system for this year.
Here's the payload system.
Yes. We like to call it air-torium. So it takes the air in and exerts it out.
Right.
And it measures all the components at all the altitudes while descending. So the oxygen, methane, CO2. It measures the components at the different altitudes.
So it's like sampling the air at different altitudes. And it has an intake where it's taking air in.
Yeah, you can see these holes.
There's the intake where it takes air in, and it samples that. It's looking at concentrations at different altitudes.
Yes.
Very
exactly.
cool. How many different altitudes can you sample?
It can start sampling it now.
Okay.
They can't hear you unless you have the microphone.
So basically, it will start after the rocket reaches apogee. The payload system will start working, and at that time, basically, it will start collecting. The pumps will get turned on, and it will constantly collect data. And after the rocket has been recovered, we'll analyze the data.
Okay. So that's why you have a single chute. You launch the rocket, it goes up to apogee.
Yes.
Does the chute come out near apogee?
Yeah.
Yes. And so from apogee all the way down, the chute comes out and you start collecting data.
Exactly.
And as you have the slower rate of descent, you're collecting that data through the sample tube to look at the different concentrations of chemicals in the atmosphere.
Yes, sir.
Fantastic.
Thank you so much.
All right. So again, wait, what's this?
This is a camera mount.
Yeah.
So we have a couple of cameras facing. Yeah, we have a couple of cameras facing up and down.
Okay, I like cameras.
Yeah, the one facing up is specifically for canard system because we want to see how actually it performs visually.
Right.
The one facing down is for the good view of the desert because we enjoyed it last time.
I like it. Okay, wait. I'm going to simulate it right quick, right? So you have a camera in this mount that's going to be looking up at the canards like that.
Yeah.
And as the canards actuate, you'll be able to watch the performance of the canards to try and stabilize the spin of your rocket.
Perfect.
And then the downward-facing camera that'll be going in this direction is for the...
It's for the desert.
For the desert. I love it. All right. Anything else? How many team members came with you?
12. We have 12 team members.
Yep.
Some of them didn't get visas, so if the India visa office is listening, please give us visas next time.
But
yeah.
say something?
Sure. Wait, you'll have like a thing? Here, let me back up. All right. It's the microphone.
Bharat Mata ki Jai!
Thank you, yeah. But we have 12 members right now. Some of them are undergraduates, a couple of master students, and we are living in an Airbnb, so it's been a really good experience.
Yep.
Everyone's welcoming, and we are really excited to be at the spaceport for the second time. And looking at every rocketeer around here inspires us, so yeah, it's really amazing to be here.
Outstanding. Y'all, it's Team 43. Here, we'll do it this way so you can see it. Team 43, all the way from India. Multiple days to get here. Got the rocket here. Good luck with y'all's launch.
Thank you so much.
Thank you so much.
Okay, if you see us out there live streaming, come and tell us how it went.
Sure. Thank you.
All right.
Thank you.
Onwards we go. Art has us another set of folks to talk to.
There's too much judging.
They're judging in that aisle right now, so we'll go to the next aisle.
OSU.
All right, OSU. Which OSU is this?
Oklahoma State.
Oklahoma State, not Oregon. Okay, so am I handing you a microphone?
Yes.
There's a microphone. Rockets, tell us about them.
So right here we've got our 30,000-foot COTS competitor.
Okay.
So it's from here down, it's all in-house carbon fiber that we have manufactured ourselves. So in-house filament winding, in-house flat plate layups, in-house vehicle layups to strengthen the joints, and a very, very light airframe that we've developed here. So it's going to give us a really good chance of hitting that 30,000-foot altitude while carrying our full-weight payload.
Yep.
Top half is just commercially available fiberglass, mostly to help with RF transmissibility. We got a very optimized design here, so very minimal additional space in here. There's just 6 inches between the bottom of this bulkhead and the top of our motor. So it's just enough space for our drogue. Same with the nose cone. Perfectly fits our parachute, no extra space. So we spent a lot of time on this rocket optimizing it, getting it nice and slippery. And so the goal here is we got a very smooth surface finish, and then a very we have a boat tail down here that's integrated into our airframe. And so the goal of that is basically to decrease our wake drag as much as possible, and basically bring the airframe back together to just decrease the drag that we're dealing with there. So through this, we've gained probably about 5,000 feet in altitude just in optimizing our fin can and boat tail. And
wait, so you gained 5,000 feet in altitude just by optimizing the exact aerodynamics?
So if we cut this off flat and had just a thrust plate there and a completely open volume, and if we had a 6-inch airframe here, we would probably only be going about 25,000 feet or so.
Okay.
But because we brought the airframe back together to just barely the diameter of the nozzle down here, it's decreased our drag so much that like we said, we gained almost 30,000 feet. So between optimizing that, our fin leading edges, and then optimizing our surface finish, we've gained a significant amount of altitude, which has allowed us to go from our original design of a 2-stage rocket down to a single-stage rocket, decreasing complexity, really giving us a much better chance of actually competing.
A single stage going for 30K?
Yes, sir.
No kidding. And you can even see, like, you've got the diameter of the main body here, right?
Rocketeers.
Oh, 1 second.
Attention Rocketeers.
Attention Rocketeers.
Launch information forthcoming. Attention Rocketeers.
Oh, good. Stand by, chat. We're listening to the announcement here. Here, y'all can look at the rocket.
Go to let your peers know. Launch information coming. Attention Rocketeers. Launch window information coming. If I could get your attention, please. All right, this goes, hello again. This goes into the vein of let's make sure we're safe. Guys, do not be driving out to the site tonight at 1 a.m. Don't do it. The gates are not going to open until 5 a.m. It's just not going to happen. Please be safe. We are talking to range scheduling, trying to get the skies opened up earlier. We will be ready for you guys at 5 a.m. Please drive safe. Don't let fatigue ruin a great week for you, especially when you're driving an hour north of here to and from your accommodations. Stay safe. So what time do the gates open? 5. You got it. You guys have a fantastic week. Good luck.
All right, official information from the spaceport there. So, yeah, no worries. So, what time do the gates open?
5 a.m.
5 a.m.
So, that's the goal, right?
I feel like I'm doing my part.
Yeah. I mean, we're hoping to get out there early, get off tomorrow. Winds look better tomorrow than they do the rest of the week. And we've got a couple other launches next week that we need to get to. So, hopefully, get this off Wednesday, at the latest Thursday. Get a good recovery going. We've done a GPS and a pretty robust ejection system to make sure the parachutes come out and stuff. So we're pretty confident we're going to bring it back, and I really would love to put it back up in the school back home. And we spent a lot of time working on it, so it turned out to be a really beautiful rocket. A lot of design time in it.
As a guess, how many hours has your team spent on it? Like crew hours?
Oh,
as a guess,
easily probably 500 man hours in it. I would say probably more than that. I know personally, I've been clocking 40-hour a week out, so I've been co-oping the last semester. So I get done with my 40-hour a week job there. I go home and I put another 40 hours a week toward this. I've been doing that since March, so you want to do the math there. I've been at it a lot, but it's a labor of passion. It's had its ups and downs. But we've got a very beautiful airframe that we've really optimized, and it's not without its faults. And there's definitely things we probably could have done better, but I'm pretty confident in it, and I think it's going to give us a really good launch.
All right.
It'll be the highest we've flown for Oklahoma State, and it's kind of paving the way for Oklahoma State. We're hoping spring of 25 next year to go for a 100,000 foot flight. So
100,000 foot flight.
We're starting here,
working your way up,
showing it, and then going the rest of the way.
Quite literally working your way up.
Yep, that's the goal. So
all right, you were Team 67, I think, right?
Yes, sir.
Team 67 from
Oklahoma State University, Stillwater, Oklahoma.
There you go. All right. Well, thank you so much for telling us about the rocket. When we're out there, if you see us out filming, come and tell us how your launch went or what's going on, and we'll see you on the range.
Yeah, appreciate it. Thanks so much.
Good deal. Good luck.
Yeah, thank you.
Okay, we are moving on. Uh-oh. Hang on a second. I'm going to hand you the microphone. Yeah. Because this is not the first time I've hung out with you. It's not. There's a backstory here that I think a bunch of people don't know. Yep. But there are not a lot of people who have sat in an SR-71 but not actually flown one. Yeah. And me and this guy. Oh, yeah. Right here. Rocket Man is what I call you. I'm Cody. Cody. You can call me Cody. Rocket Man, we actually met up at the Evergreen Museum. How many years ago? Probably close to 7. 7 years ago. I was probably 11, 12. Yeah. And now I'm doing this. We were doing a thing at Evergreen Museum. We came out there to do a virtual field trip, and you actually had your grandma or somebody. My grandma drove me up. Yeah. Your grandma drove you to the Evergreen Museum to come and hang out with us while we did the virtual field trip. Yep. And while we were there, we were looking at the SR-71, and Julia, the person who set it all up, got Cody and actually sent Cody up the ladder and had Cody sit in the cockpit of the SR-71 with me because you came all the way out to the museum. Yes. So I've known Cody for 7 years now. Yeah. From Twitch. Sort of met on air quotes, met on Twitch. Yeah. Rocket Man 1, 2, 3, 4 is what But now, after all these years, you're here at Spaceport America and you have a rocket that y'all are going to try to fly. One thing you don't know, in 2017, I believe you live streamed Spaceport America. You showed Oregon State University's team. Yep. I was watching that stream. Nice. And I knew I wanted to attend Oregon State University and do this competition because of that. Again, nice. Yes. I love it. And here you are. Yes. It wasn't just a dream. Like now you're part of the other OSU, the Oregon Oregon State.
Oregon State, yes.
Not Oklahoma State.
It's very
Oregon
funny.
State.
They put
Why
us
are
right
they
next to
each
each
other?
Alphabetical order. And we also have black and orange. It's so
black
confusing.
and orange rocket, black and orange. Seriously,
It's never confusing.
And also, we used to be OSU-AAA.
Yes. And now we're OSU-AAA.
So we're here. You've come all this way. You have a rocket.
Yes.
What's going on with your rocket?
We drove for about 24 hours. We brought a rocket. We brought a 34-foot launch rail.
A 34-foot launch rail?
Yes. We're gonna set it up. It's gonna look great. Okay. So I'm just gonna say this has been a journey. This isn't just an engineering task. It's been a journey.
A journey.
Yes.
Tell us about the journey.
Thank you. Okay. So this is our lower aft body tube.
Yep.
You're gonna notice it looks a bit odd. We got
it's got like chines or something. What's going on here?
We're calling these strakes.
Strakes.
Yes.
Okay.
So during our first test flight, going up.
Yep.
10,013 feet. Great altitude.
Okay.
Drogue deploys.
Okay.
Great. It's coming down 1,500 feet, 1,000 feet, 500 feet. No main. So luckily we had an oversized drogue, so most of the rockets survived. We had to cut a foot of body tube off. Now that foot of body tube...
So the impact damaged it and you cut a foot of body tube off? Okay. Which changed the stability of your rocket.
Exactly. It moved our center mass down. Yeah. No, you're good. We had to move the center mass got moved back.
Yeah.
Which reduced our caliber's stability. So we had to add some fins. You might think, oh, Cody, why don't you just add similarly sized fins? Great thing you asked. You see, if we put this back in the composite oven, there's a chance that our back fins could delaminate, or something bad could just happen. That's our luck.
Come apart.
Yeah. So instead of doing that, what we did is we thought, okay, there's a phenomenon called fin flutter that we're mostly fighting.
Yep.
The two things that fin flutter hates: short fins, long fins.
Long body contact.
Yes. So
and short lever or moment or whatever you want to call it. Like short fins. Yeah.
Yes. So the long body contact allows for more bonding, which keeps our fins strong.
Wait,
you can toss that around. It's not. I'm not
glad
worried
it
about
didn't
that.
break off when you did that. You're like, oh yeah, and it comes off. Okay.
There is an integration step to check that the fins are indeed attached.
Right.
Yeah. But yeah, that's our aft body tube.
Okay.
We are a 10K SRAD team. I should have started with that.
So this is just half the rocket right now.
This is half the rocket. That's the other half.
Oh, the other half is back there behind you.
Yes, we're a 10K team with a 13-foot tall rocket, which is a little bit extra. The reason for that is, at Oregon State University, we have 3 rocketry teams. We have the high-altitude liquid engine team, we have the high-altitude rocketry team, and then we have us, Ezra.
Okay.
And so the liquid engine team is going to do their subscale, and they kind of just changed up their diameter a little bit. So they couldn't use their body tube, and we're like, we'll take that off your hands. We got it.
It's like hand-me-down body tube?
Exactly.
Hey, we'll take it.
This is a nice body tube.
It's very budget-friendly.
Budget-friendly choice? Because it was a nice choice. But that's why it's such a big diameter, such a long rocket, even though we're only going to 10,000 feet. If you look at the poster here, there's a significant portion of open space.
We refer to the poster again.
Yes.
Nice.
It's hard to see X-ray, hard to do that.
But all this is open space, is what you're pointing out.
And
like
if you think of a seesaw,
think
of a seesaw. We could put a little bit of weight up top to counteract this big weight down here because we have a long lever on. Yeah. So the longer the body tube, the less weight we have to put up top. That's another reason why we had to kind of put these fins on. We didn't want to put an extra 2 kilos in the nose.
Right.
Yeah. Speaking of the nose.
Wait, why is that a Snapple?
This is our ballast system.
Wait, what?
Yeah. This is flown. This is one of the only parts of the rocket that was not changed after the first test flight.
Tell me that's sealed. What is it? Are you going to put rocks in there or bolts or what?
We have BBs.
Certainly not putting Snapple in.
No.
Not sponsored by Snapple.
No, not sponsored by Snapple.
Okay.
That's why you have the tape.
That's why you have the tape. You can't tell what this is.
No idea.
So you're going to put like shot or BBs or something like that in to change to fill it up?
Yes. Not all the way.
Okay.
Last time was about 3/4 full. Hopefully we only need to fill up to below the label. We only need a couple. We need 100 grams of ballast.
Okay.
Not that much. We're doing pretty good this time with
Are
these
they
fins.
loose?
They are loose. So that was something that we talked about during the first test flight. What happens if, the rocket starts turning?
I've seen The Martian.
Yeah, you've seen them. I was thinking about that. Yeah. So we've determined that it's at such an angle.
Right.
That if the rocket was already at that angle, something's going really wrong already. So, because the BBs, they kind of stay together. Once you're at this angle, if you go past this, your rocket should never be past
you're
that.
Already in trouble.
Yeah. Or you're pitching over for apogee.
Right.
Which both are nominal things.
I like it. Normal is like endemic here.
100%. Yes.
So, did you calculate how much mass you need to put in there, and you're using that to shoot for the target, or how do you know how much mass you need?
I'm glad you asked, Ross. You see, our team is doing a little funny, and here we have beeves.
Do you have a what?
We have beeves. I will elaborate here.
Okay, please.
Oregon State University has Benny the Beaver as our mascot.
All right.
And we have the Beeves air brake system. And if you look over at the poster, front of the poster, yet again.
What am I looking at?
The blade extending apogee variance system.
Beeves, there it is.
Yes.
The blade extending apogee variance system.
Yes. So Beeves is our air brake system. It's using a rack and pinion and a PID loop to calculate its apogee and then bring it down to 10,000 feet.
Gotcha. So we've seen this on a couple different rockets. Yes. If you calculate that you're overshooting, it's going to extend some air brakes there. And if it calculates that you're coming in under, it'll keep it tucked in so that you have all of the, the minimum drag. And you keep all your mass, your energy, yada, yada, yada.
Compared to the 17s, these are huge air brakes. They increase.
They look very beefy. Like,
let me fold them out.
Why are they so beefy?
Let me set down the mic.
Oh, here.
Can you hold that real quick?
There you go. Why are they so beefy?
It's overkill.
It's overkill.
Yeah.
They look like load-bearing air brakes. Well, I guess technically.
Technically.
Whatever.
So we really wanted to go overkill with this stuff. We could bring the altitude down if we needed. We are probably going to only use 40% of this. It increases the surface area of our rocket and drag force by 150%.
Wait, really?
Yes.
When they're fully deployed?
When they're fully deployed. It is a
kidding.
crazy amount of braking force.
It doesn't look that. Why? There's a nice sticker, by the way.
Yes, there are some nice stickers. We have the rockets. And you can also notice we have a custom PCB. It's a U-shaped PCB.
It is a U-shaped PCB.
Raspberry Pi.
And it actually says Beeve on it.
Beeves V4.
Beeves V4 on it. I think y'all can see that. Yeah,
this is kind of the fourth iteration the university has tried at an air braking system.
Okay.
Yeah. So this is our team lead's baby.
All right.
He has done so much on this. Also, Dexter over there. He's the
wave, Dexter.
He's done MATLAB.
He's like Wilson on the other side of the fence.
He's done so much MATLAB. They've done so much to try and get this to work. It's going to be amazing to see it fly and hit 10,000 feet exactly.
I like it. It's like he's done so much MATLAB. How does that make you feel?
It makes me feel pretty good, honestly. It's been actually really, really fun. It's been probably one of the most enjoyable things I've done in college so far. So, yeah.
Good deal. Like you're hiding behind the board there. All right. So we've got the rocket. We've got the top of the rocket, the pointy bits. So we've got this. What else are we looking at?
So we got here, we have our camera nacelles.
Ah, yes.
We have 2 run cam split 4s.
Okay.
We're a little concerned about overheating. We have 4 hours of battery.
That happens.
Yeah, it happens. Yeah. I'm sure you know camera stuff in the desert in New Mexico.
They like to overheat.
Yes. These are positioned right above the air brakes, so we're getting a really nice shot of the air brakes.
Of the air brakes coming out.
Nice.
Now, wait a second. Is it just recording or is it a live feed?
It's recording.
Maybe next year.
Okay, we did think about this. We're 11 people on the team. This is our first year back. No one knew about how to do rocketry.
Yep.
And so we just didn't have enough time.
It's all good. I'm giving you a hard time.
Yes.
I like live cameras. I'm just saying.
Just a little bit.
That's what we need. We need a live camera off of a rocket one of these years.
I think there are. There's some teams around here that are doing them.
We need to find them. So I want. What's going on here? This is just a launch box. That looks.
This is a launch box we have made to comply with launch standards, so we can safely do launches. Because we don't want to drive down to New Mexico every time we want to launch. We don't want to drive to Fall every time we want to launch. We want to go to a local place. So it's 3-4 hours away. Right? It's in the middle of the Oregonian desert, the high desert. It's called O-Rock.
Did you just say the word Oregonian?
Oregonian
desert. I guess that's what you call it.
It's
really thought about it.
Yeah. It's over the pass, so it's pretty far away.
Gotcha.
So this launch box here, we have our deployable key.
Nice. It's on like a little string, a lanyard.
We don't want to power it on right now. It's
Don't
going
do
to
that.
transmit radio signals.
Yeah,
you
yeah,
can turn it and then you press fire. This shows what if you have radio contact with the other box, which is over here.
Does that go with the rocket at the pad?
Yes, this would be at the rocket at the pad.
I like these, like straight from Harbor Freight.
These are named Gooper and West Systems 105 for the epoxy.
What? Gooper and West Systems 105.
Yeah, that's named after all the epoxy, all the nights epoxying the fins on, stuff like that. It's been fun. But we have indicator lights on here telling us we have continuity, stuff like that. So, yeah.
This is the other part that I haven't seen.
Okay.
Like, what's going on back here? What is this?
This is probably where I have to break it to you. We kind of dropped the ball on payload. If I'm being completely honest. Okay.
That's the payload.
That's the payload.
It looks like washers.
It's because you're very observant.
I'm very observant. I've been doing this a couple years.
Yeah.
That's the Home Depot payload.
Yes. I didn't know you could guess the name like that. So we had a big old plan to make a giant payload.
Of course.
And of course, the plans fell through. We decided to focus on making a good launch vehicle that's going to achieve our objective goals.
Yep.
And this also achieves our objectives.
Sure. It's mass.
Yeah,
it's a mass. I can't do the mass simulator joke again. I've done that too many times already. It's actual mass.
We have a sensor. It's recording atmospheric data on carbon dioxide and NOx gases.
Oh, I was going to be like, yes, it's still mass. That's what the sensor is recording. Is like, is it mass? Yes, it continues to be mass.
Did
if
the mass
it ceases
disappear?
to be mass, we're in trouble.
That would be bad.
You'd probably win, though, the science competition.
Yeah, no, 100%. So we have our sensor on here. It runs great. It's great. But we kind of need 8 more pounds. This is about 50 grams. We need a little bit more on there.
A little bit.
And it fits in CubeSat form factor. So it's great. It's awesome. Love that. Love to see that. And then up here we have an example of one of our interrupts.
Yep.
So we're so excited that we get to actually have a move for our flight times. Every aerospace engineering student puts these on their backpacks.
It's what they want.
But they never get to use them. And we finally got pull pin activated for the cameras, for the AV bay, for the dual redundant flight computers.
Is that the power? Like when you pull that pin, it sends power to all those systems, or what is that?
So this one specifically is for the cameras. So when you pull it activates the cameras and they start recording.
Gotcha. And they start recording?
They start recording, yes.
Nice.
That's a little quirk on the run cams. We didn't. You need like a drone controller to edit the flight cams, and like it's a little complicated. So we just have them on the base setting, which is they start recording as soon as they get power.
Makes sense.
Yes.
All right. We've gone all over the rocket. What is going on here?
We must cover one of the best parts of the rocket. This is the parachute. We have made a homemade parachute, as you can tell. Yes. And we have our leopard print right there. We have the hot pink. We have the black. It's going to be observable from so far.
I like observable.
Yes.
Like sometimes teams come out here and they're like, oh, what's a good color for a rocket? Sky blue. Like, what color should I make my parachute? Sky blue. And it's like, that's our team color.
I'm going to paint my rocket camo.
Yes, exactly. Desert camouflage and sky blue is what I'm going to paint my rocket. I am a fan of the hot pink because it will be very observable.
Yes. Yes, it is. Yeah, it's also a little funny, so we like it. We love it.
Okay, did we miss anything else? We have lots of other teams to talk to.
The motor, just one last thing.
The motor.
We don't have it here because no energetics in the building.
No energetics in the building, I saw the signs.
But we have a SRAD motor. The beginning of this year, we used something called we have a stainless steel nozzle.
Right.
Which is crazy because not a lot of teams do this. The university had banned us from using graphite, from machining graphite and phenol.
They banned you from using graphite?
Yes.
Feels like there's a story there, but go on.
Yeah. So we were like, what do we do? So we were like, stainless steel?
They banned us from using stainless steel.
Yeah, exactly. Machine shop's just going to close down at that point. But EEE does not allow these, and because we cannot use our own rocketry insurance here, we have to abide by EEE rules. So we do have a commercial off-the-shelf nozzle that is about the same geometry.
Gotcha. So you SRADed.
Yes.
SRAD, it sounds like a verb.
Yes.
Your own motor.
Yes.
But here, for compliance, you're going to use a COTS motor.
No. It's still SRAD.
Oh, it's still SRAD.
It's a COTS nozzle.
It's a COTS nozzle.
It's a hand-mixed propellant grain. Still a handmade propellant tube.
Okay.
Different nozzle.
So it's just the nozzle that's different to get you into compliance for safety here at this event.
Yes.
Number of teams, yada.
Yeah.
Fantastic. Awesome. All right, Cody, we are going to move on to some other folks. We'll find you around the launch pads.
Yes.
We're going to be out there as as well. If y'all know when you're going to set up, like try to find me, or you know how to message me, because we're going to try to embed with some teams.
Okay.
But if we can come embed with you
Oh,
and see you get set up and see your launch, it would be fantastic.
100%.
All right, folks, it's Team 68, all the way from the Oregon State University. My buddy... Is it weird if I call you Rocket Man?
It's not weird.
Like your friends are like, oh, dude.
They know. They are aware. They're aware of the hygiene.
It's Cody.
It's Cody. It's Rocket Man. Whatever you want to call
Whatever works.
Yeah.
All right. It is so good to see you out here. Your team working on this rocket. And there are more people.
Just
By the way,
everyone.
wave. There are more people on the team. No, you're not on the team. You're just waving.
We actually transported their motor all the way from Oregon. So
good teamwork.
Yeah, exactly.
All right. We are going to move on and talk to some more teams, but we will see you out on the range.
Thank you.
All right, got it. I am going to step this way for a second. Folks, I don't know if I'm going to flip the camera around. Let me try. There you go. So this is what we're doing out here. It's the Spaceport America Cup 2024. I've been out here for 6, 7, 8, I don't even know how many years I've done this. Even before I was with NSF, I was out here helping Spaceport, helping Ezra live stream these events. I was just like, hey, can I come and live stream your rocket launches? And they're like, what are you talking about? And I'm like, no, I don't want to charge you for it. Just give me access and I'll come and share this with people so people know what's going on. We've been doing this for so many years now. Now that we're out here with NSF is a sponsor of the event here, going around, catching up with some of these teams. I am interviewing teams right now, but I'll tell you, the only reason we are able to do this, like take time out of our schedules to come out here and support the teams and share this with y'all, is because y'all keep showing up. I'm going to wave the microphone at y'all. Y'all keep showing up with us. You support what we do here at NSF. I'm not going to talk about it too much. Let's go to another team and see if we can't do some more student interviews. We got about 30 minutes. I don't know if they're... I think that one's about to shut down. We have a little bit more time here, but let's get some more teams in. I feel like, where am I going?
That way.
Am I going that way? I'm following that guy. Okay.
Right that way.
Thank you. Art, where are we going? Literally in the middle of the crowd. Okay. They good to go? Hi! Can I talk to you about rockets?
Absolutely.
Here's a microphone.
Yes, please. Hello.
This is my phone. You can get that. So what team number are you?
We are Team 72 from Purdue University.
From Purdue University.
Yes, sir.
How many team members do y'all have out here?
We have 22 with us this year.
With you?
Yeah, with us.
Is that the entire team, or there's more back home? Or?
There's more back home. We got probably 20 more back home.
Okay, are you doing gang signs?
No.
No gang signs?
Peace signs. Peace signs.
Just peace signs.
They're UK viewers.
We love you.
I'm so sorry. I had no idea.
You didn't know. Anyways, moving right along. So you're a rocket. You've come all the way out here from Purdue. I'm pretty sure that's somewhere on the East Coast, right?
Indiana. Close enough.
Not okay.
Not quite.
Made it all the way out here. Dead center. Tell us about your rocket.
So this is Project Midas. It's about 10 feet tall, about 58 pounds. We're flying 10K COTS this year, which means we did not make our own motor, sadly. We were close, but no cigar. It's going to go to about 10,000 feet, and it's got dual deploy. The drogue will deploy at apogee, and the main will deploy at 1,000 feet. Am I missing anything?
What apogee are you shooting for?
10,000.
10,000. Okay. So hopefully we get drogue at apo.
Yes.
And then we get main at 1,000.
Correct.
So you don't have to go 20 miles downrange to try and find the rocket.
Oh my gosh! Please no. Please no. That'd be a trek.
So I noticed that the top of it is slightly larger diameter than the rest. How did you come to that conclusion?
Very astute observation. Well, first
I do this
of all,
for a living. Like
nothing gets over your head. Well, first of all, we need to fit our payload up there to make a CubeSat to meet requirements. So we needed a 6-inch diameter up top for that.
Okay.
But in anticipation for SRAD, we wanted to make the bottom more lightweight. So we cut down 1 inch of diameter to reduce weight for SRAD to get us up as far as it could.
Gotcha.
Of course, as I said before, SRAD didn't happen, but we kept the transition because we think it looks kind of sick.
So, did you buy this? Did you make it all yourself? Like, tell us about the parts.
So, we bought all of our main body tubes. These are all fiberglass from Wildman. Shout out Wildman, we love him. The nose cone we made ourselves, fiberglass slay-up, aluminum tip. The transition is made out of 3D printed filament, PET-G on the outside for thermal
So that's
resistance.
the transition where it changes diameters there, right?
Exactly,
Gotcha.
exactly. The fun part about that is the outside is 3D printed, but the inside is what takes all the load. So the inside has a fiberglass tube through it and some centering rings. So that disperses all the load from the thrust of the rocket rather than relying on 3D print.
So that's more for aerodynamics than for load-bearing capacity or whatever the engineering term would be.
Exactly.
Okay, gotcha.
Yep. And then our fins are homemade fiberglass layups, and then we did some tip-to-tips on top of it for aerodynamics and stability.
All designed yourselves?
Yes.
All designed yourselves. I love the fact that I come out here and you're like, oh yes, we needed room for a payload, and then he's like over here picking up a payload.
Oh my gosh,
so
he's on it.
Is this your payload, or is this...
Do you want to talk about this?
Sure.
Actually,
Sean, you're the payload. Somebody here, payload. Get in here. All right.
So this payload is a collaboration with another team, the satellite team from Purdue. And the idea behind their payload is that this is a satellite that they will take care of the electronics, and then any experiment that a professor or other team wants to send to space, they hand it off to this team, they put it in the top part of this box, they deal with everything else, and they ship it up to space for you.
So wait a second, it's almost like a provider, like a service provider?
Exactly. And so what we are doing is we have a mock experiment in here, which we're basically testing the shocks on it, the temperature, things like that, to make sure that it satisfies the requirements during launch and protects whatever's inside here properly.
Whatever's inside here, because you're like doing it, I say as a service, but you're designing the environment that it's going to be in, and then somebody else designs the payload to go in there.
Precisely.
It's almost like you have a launch user's manual that describes how that works.
Exactly. This is the vehicle, and anything that wants to go in it can.
Excellent. And this, again, all designed by y'all?
Correct.
3D printed, machined. I feel like I could figure out myself, but you tell me.
This is all machined parts. Various different processes involved.
Okay.
Let's see, what do we have here?
So I'm curious, right? I'm curious. That is sort of a container, right? But the payload fits inside of that. So is that a standard, like, CubeSat-sized container? And so the thing that goes inside is not the standard size. Talk to me about that a little bit.
So all of this is our payload, which is a standard 3U sizing.
Right.
And then the team that kind of designed this idea, what goes inside here is a 2U size.
Gotcha.
And that is like the top 2/3 here.
The top 2/3. So are you providing, I'm going to use services, are you providing any services with the last part of it there that supports the payload, or what is the bottom part?
The bottom part provides the electronics.
Provides the electronics.
Yes.
All right. And so this is actually flying on your rocket when you launch it?
Yep. Yes.
Going up to like, I cheat. I look at your name tags because your name tag says how high you're going, and I can't memorize everybody's. I'm just like, going up to 10K, right? Yeah. So you're delivering this up there. Are y'all also getting telemetry back, or is it recording locally, or?
This is recording all of the vibrations that it experiences.
Okay.
And then when it comes down, we recover that, and we send that to the other team to kind of look at and say, is this what the vibrations we expected, or is there anything new here?
Gotcha. Did they get to come, or y'all just came?
We came.
You came. They stay home in the air conditioning, and you'll handle the lunch.
Exactly.
You've just picked up this.
Yes.
What is this?
Avionics bay. This is our avionics bay right here. So, Kale, you want to take it over? Absolutely. Oh, man. All right. So on the avionics bay, this is what's transmitting our altitude, our GPS, and everything you would ever need. So we have our main right here, which has all of those things, and this one is our redundant. That's everything except for the GPS. And this is all the commercial side, but on the other side, a bit more funky, we have our student research and design side, where we have our own radio module. It's all controlled by an STM32. We have our files saved right here and our GPS right here, so that way we can test our own data and see what kind of stuff we can come up with.
Gotcha. Are they color-coded?
No.
It's like the commercial side is one color, and then the astronaut side is the other color.
Yeah, little
this
known.
Is the commercial side?
Yeah, little known fact. Purdue's colors are actually black and purple. They don't tell you that.
That's not true at all. Don't listen to him.
I'm looking at the side, and I'm looking at your shirts, and I'm wondering if I should believe you.
Yeah, no, I think you're colorblind. This is yellow. This is gold.
Yellow and gold. Nice. So avionics, there's two different sides. Is one's the COT, so you bought that off the shelf, and you designed the other. Are they redundant? Are they performing different functions, or what's going on?
Yeah, they're just getting sensor data. They don't control the charges at all. This is just something that we want to experiment with and see if we can get better results than what we can find on the COT side.
Gotcha. So two different things, but that's mostly like recording what's going on with the rocket,
Absolutely.
as opposed to controlling the rocket.
Yeah, absolutely.
Nice. I like it.
Very perfect.
All right. What else haven't we looked at? We looked at the payload, which was over there. We looked at the avionics. Yeah. Did y'all bring extra nose cones or what?
All right.
What is this?
These are actually a research project that we're working on right now. So the idea is basically what can we do with airflow inside of a rocket? So the flow goes through the rocket down here, and then as it goes through, we have a turbine that it will hit. And as the turbine spins, we have a generator on the inside around here that would then charge a battery that's like used for backup storage for power, or can be powering some other sort of component that's up towards the top of the rocket.
I like it.
It's not super great for solids just because it's not as necessary, but for liquids or for hybrids, it could be super useful. And then as it goes down, one of our previous iterations for a payload design was actually a heat transfer device. So we would have fins, and the air that's passing through the rocket would then pick up that heat, take it away, and then cool down the inside. So that could be used for like avionics or something else like that. And then as it continues to pass through, we would have a transition similar to the one that we have right here, except this one would have holes in it. So then the area would match the same profile as the front of it right here.
You can actually see through that. I couldn't see that when it was on the table. Nice.
So the holes would be the same area, so that way you don't have any problems as far as like compression or anything like that.
Right.
And the air can flow freely through the entire rocket. And then as it comes out, it actually reattaches the airflow that comes off of that transition a lot better than it would otherwise. This actually gets used a lot in commercial flights right now, but it hasn't been ever implemented into a rocket as far as we're concerned.
Nice.
So that's what the idea is as well.
I like this. Like when you were explaining the turbine system and stuff, I'm like, it's the world's most complicated cell phone charger. So what you do is you put your cell phone in the rocket, and then the rocket launches, and the air goes through there, and it spins the turbine, which goes to a generator, and then it charges your phone.
I mean,
that's not actually what happens.
That could be a brand new payload right there.
It's like, need to charge your phone? Here, put it on our rocket.
Yeah, exactly.
I'm not sure that idea is going to take off.
Maybe. We'll see. It depends on how many phones you can get up there. If maybe we just put someone into the rocket as well. Then anyway, you can charge your phone while watching a movie.
While you're on the internet.
In-flight movie.
All right. Well, good deal, y'all. This again was Team 72 over here. Purdue Space Program. It says Purdue Space Program, which is not on the East Coast, as it turns out. When y'all are out on the launch pad, let us know. If you see us out there filming, flag us down, tell us how it went, but good luck on the field.
Absolutely. Thank you so much.
All right, y'all. Thank you so much for hanging out with us. Y'all have like a cheer or anything? No,
boiler up.
Boiler up. They're just going to say boiler up. All right. Art, I need you to hold the camera for a second. Okay. And just point it like at a thing, because I need to plug in my phone or I won't be able to read what's going on with chat. So just aim at your rockets or something. Which pocket? It's in my backpack. Chat, stand by. I need to plug my phone into external power. So that we can keep going until they kick us out. I may have just jostled the HDMI cable. And we're down to 17% internal power on the broadcast unit.
Clear now, because everyone has to be out by 5.
Out by 5? Okay, cool. And it's 3:40 right now, so we'll probably go until about 4 o'clock, which was our plan, and our battery should get us through that. Let me plug in my cell phone real quick, and we will continue on. There's that. That goes in there. Make sure I'm power positive, or it's going to turn my phone off. Well done. Whatever. It is charging my phone, though. I waited too long. Let's do the next interview, but I will not be able to watch chat this time. But I will just stow my phone, and we'll do the next interview. All right, backpack back on. Oh. And we're talking with these folks next? Queen's University. All right.
They tracked me down.
They tracked you down. Okay, good deal. There's that.
Wonderful.
Okay, give us 1 second. We may have just broken everything, but let me make sure nothing's broken. I can't actually read it. Can you? What? Is the stream still working?
Oh, you guys live streaming this?
Sorry?
Live streaming this?
Oh, of course.
Awesome.
Yes. Give us just 1 second, and then we will chat.
What if I say no?
Well, I mean, the microphone back. It's fine. Like you can say no. It's absolutely cool. Next. Look,
What was like the interview?
That was it right here. Like they'll just go again. You know something? I don't want y'all to start talking if I've just jostled a cable. So give me just 1 second here.
That's totally fine. Yeah, you're good.
Which team number are you?
73. 73.
73 from Queen's University. All right. Did you get us over there? NASASpaceflight. Yes. I was trying to get to my phone before it died, but my phone died right as we walked up to you.
That's super unfortunate.
There's our channel. There we go. Ezra interviews. Are we still good? Survey says. Oh, well, I see you.
Oh, hi.
I think we're good. 5 by 5. Okay.
Great.
So I didn't want you to go through half the spiel.
I'm happy to do that. Don't worry.
By the way, we didn't know. So, Queen's University, tell us about your rocket.
So our rocket is a 4.5-inch diameter rocket that we made entirely ourselves. So everything except the motor is made by us. So it's a carbon fiber layup with a fiberglass area for our avionics section. So that'll be these parts up here. And then we've made it cow print because our theme is cows, and its name is Bessie.
Okay.
There's a long story associated with that, but it's really fun. So yeah, we're aiming to launch 30K COTS motor, tomorrow, hopefully, yeah.
30K COTS motor?
30K COTS motor, yeah.
No kidding. I'm not a rocket expert, but... Oh, there it is.
Yes.
There's the pointy bit.
We have our payload that fits in here, and we do lots of fit tests and stuff like that, so we tend to keep it off of the rocket. And then it looks like it has 2 tips, but it's just a 3D printed tip to cover the really, really, really pointy tip.
It's
underneath.
like a clown hat.
It kind of is, yeah. Exactly.
That is a very pointy rocket. Like, why is it so dangerous looking?
So we, with the motor and the weights and everything that we do, we end up going Mach 1.72. Which is fairly fast.
Okay.
And so in order to do that, we try and build it as aerodynamic as we can. So that's why you see a really, really tall, really, really skinny rocket.
Really, really tall, really, really skinny rocket.
Exactly.
And that probably goes into the tip there as well, huh?
The nose cone?
Yes, the nose cone.
Exactly. So the payload gets fed through and then mounts into the aluminum tip with threads.
Got it. So does that sort of screw onto that thread there?
Exactly,
oh,
yeah.
Well, there, it apparently
and there's
comes off.
a couple inches of thread that lock in there
that
to
lock
keep it
into
on.
there.
Yeah.
No kidding. And then because of the speed you're going, does that dictate the material you need to make the tip out of?
Exactly. So in the past we've used stainless steel, but aluminum is totally fine. We only use stainless steel if we need the tip to be a bit heavier for stability.
Okay.
So we have an aluminum tip this year.
So this is aluminum.
Exactly.
So the speeds that you're going, you're not going to melt that tip off or anything?
No, we did have to check though, because we were a bit worried, and that's why we can't use composites for our tips at all.
Yep.
So we have to use machined aluminum.
You did the math.
We did the math.
Did the math.
Yeah.
All right, so this payload, it looks like it dispenses beverages or something. Why does it have a hose in it?
Almost. I'll pass it over to Joe. It's his payload as he's payload team lead. And so, hey, Joe.
By the way, y'all did a fantastic job lining up here so I could get you all in this shot. Joe, tell us about the payload.
Sure. So this is our gas recognition unit. Basically what it does is it intakes air samples during the rocket's descent, and using an array of electrochemical gas sensors, which are located on the sensor board here, we're able to take measurements of the composition of the atmosphere throughout the descent. So we have these 2 boards that we've designed with our team. This is our sensor board. Our motherboard here controls the logic of these solenoid valves and this air pump, which allows us to control when these 2 gas collection cells, so there's one gas gas collection cell here, one gas collection cell above. When these gas collection cells actually get filled and when they exhaust, and doing so, we're hoping to be able to plot the composition of the atmosphere over the altitude of the rocket.
Gotcha. So you said an air pump, so this is like an active sampling. It's not a passive sampling where the air just gets in there.
Correct, yes.
At some point, you trigger the air pump,
exactly,
and it begins to flow the air into the sample chambers.
Exactly, yes.
I made up some of those words, but I'm close?
Yes, very close. Cool. Yeah, so we're using this motherboard to control the logic of when this air pump gets activated, when these solenoids get activated, to control which cell gets filled, when it gets filled, how it gets filled.
So how many cells do you have that you can sample from?
We have two. So we have a lower one here and an upper one here.
A lower one, are those the two?
They're the two gas collection cells. They're very skinny because we don't need actually too much, that much of a volume to be able to take samples from our electrochemical gas sensors.
And so how are you actually sampling that? Are you trying to fluoresce it or firing a laser at it, or how are you trying to figure out the concentration?
So our electrochemical gas sensors actually output a current based on the concentration of the atmospheric pollutants that we're targeting. And based on that, we're able to convert that to a voltage, an analog voltage, using a bunch of op amps. And then using that, we're able to send that data to the motherboard, and that motherboard is able to log that data, and we're later able to convert that voltage to a concentration of atmospheric pollutants.
Gotcha. So you pre-calibrate this, and you say, what's going on here? Really?
Yeah,
lever
wiring
nuts?
that still needs to be
like,
finished.
Not Wago lever nuts?
Yeah.
It's for rapid development is what that is.
Exactly.
If it ain't broke, don't fix it.
If it ain't broke, it's going to be broke if you keep using those. But no, seriously. So you're sampling this, you said, on the descent.
Correct, yes.
So this goes up to Apo, it pops a drogue, it starts coming down. Yep. Is it timed? Is it controlled by a barometer? Like, how do you tell it when to start sampling?
Right, yeah. So our motherboard actually has an onboard altimeter, which is very similar to the one that our avionics team developed. And so using that, we're able to determine when we reach apogee, as well as detecting launch events such as takeoff, drogue deployment, main deployment, and landing. And so we're using that to actually time when we're taking in our samples.
Gotcha. And I'm going to go out on a limb and guess that y'all developed this system.
Correct.
All right, I haven't seen it at like Home Depot or whatever.
Yeah, we looked hard, but we couldn't find it.
We looked hard. It's like, what aisle is this in?
Yeah.
So y'all have completely designed the payload as well?
Correct, yeah.
All right. Are y'all ready to launch?
We hope to be ready by tomorrow.
Well,
yeah,
the payload's
maybe Abby can talk about that a bit more.
So we are actually developing our own flight computers. So we have a fully COTS system in place that has been safetied. We've been issued our flight card, which is super exciting. But we want to make sure that eventually one year we can use our own electronics. So we're trying to get some boards flight certified in this launch. So if we're able to develop them today, we'll launch tomorrow. If not, we'll launch one of the following days. Yeah.
If we're able to develop them today.
Hey, finish developing them. Finish developing them.
That's not what you said.
That is true.
So you have COTS things that are already certified to fly the rocket.
Exactly.
But you're still working on finalizing. We have a lot of the SRAD systems done, but we are a unique team in the fact that we put a lot of sensors on board. So we have a sensors module with many, many sensors, and we're just working on making sure that that code is reliable. Gotcha, making sure the code is reliable. Always important.
Exactly.
All right. Well, we are going to continue going along here.
Wonderful.
Best of luck with your launches.
Thank you.
If you see us out there where we're running around like this,
we'll be sure to stop you to
come
chat.
up and tell us how it went or what you're doing or whatever. Like, oh my gosh, we keep trying to finalize this code or whatever. Just catch up with us and good luck with your launches.
Thanks so much.
All right, y'all. It was Team 73.
Team 73, Queen's University.
Queen's University. Thanks a lot, y'all.
Perfect.
I'm going to take this from you, then we're just going to like walk over there.
Sounds good.
That was awesome. Thanks, y'all.
Thanks. Okay, everyone down that way with a rocket is being judged right now.
Is being judged right now. Okay, and folks, they are starting to clear out here, as you can see by this stuff. But let's go back this way. We are going to be getting close on some of our battery margins here, but stand by. They are supposed to be out. I think they're supposed to be out by 5, but they're starting to clear out at 4.
Yeah, judging ends at 4.
Judging ends at 4. Okay. Let's pause here for just 1 second and check our battery levels. I mean, there's just people carrying rocket parts around. Like, look at all the rocket parts. We did talk to those. I just don't want to get halfway through it and then not have battery. So let's go over here. Yeah, sure. All right. I'm going to look at this rocket on the table.
Yes, we want to. We're running out of people. I know, everybody's leaving.
All right. We don't actually know how much battery we have left right now, so I'm going to hand you a microphone and then be rude and check my phone. All right. Am I handing this to you?
Hello.
Okay.
We're from University of Arizona in Tucson, Arizona.
And a team number?
95.
95. All right. Team 95, University of Arizona.
Yes.
There it is. AIAA. Tell us about your shirts first.
Well, we put it into a Hawaiian shirt generator, our logo, and created these awesome T-shirts. I gotta say, or Hawaiian shirts. I gotta say, it's definitely the #1 compliment we've gotten on our rocket. That and the octopus on the nose cone.
Why is there an octopus on the nose cone?
It's become somewhat of a mascot for us. It was just a natural way of things. Perfect protector. So yeah.
It's a nose cone tip protector.
The serious answer here.
Yeah.
So where are you all headed to? How high?
10,000 feet.
10,000 feet. You make your own motor or buy one?
Off the shelf.
Commercial off the shelf.
Yep, this is a fully off the shelf rocket. It's our first year.
Yep.
And we're just happy we made it.
You're happy you made it. So this is the first year you've made a rocket, come to Spaceport, like qualified.
It's the first year our club has gone to Spaceport since 2017. So all of us are new, and it's an experience.
It is an experience to come out here. All right, why is the name of your rocket Fire Hazard 2? Like, you have experience with fire hazards, and this is the second one.
Well, so we won't talk about Fire Hazard 1.
You probably shouldn't talk about Fire Hazard 1.
But this rocket, although we passed safety inspection, could be a hazard in many ways.
That's true.
And fire is one of them.
Fire is one of them. If everything goes well, fire should be one of the things that happens with the rocket. Tell us about the payload. Are y'all flying a simulator?
Yep,
or an actual payload?
It's a 3D printed block full of rocks.
A 3D printed block of rocks.
Yep.
Nice. So we always joke, it's like, oh, a simulated payload. Well, no, it's an actual payload. Like, it is a block of rocks. You're sending it with a rocket, right?
We're going to see what happens to rocks at 10,000 feet.
We're going to see what happens to rocks at 10,000 feet. Mm-hmm. What else about that? I mean, this is the first time y'all have been out here in quite a while.
Yep.
Do y'all go to other competitions, or?
Well, our club in the past has been more of a hobby club.
Right.
We make level 1 rockets, like this one, which is our 1/3 scale model of our big rocket.
That is definitely different.
We built that to test out the aerodynamics and also the flight computers and stuff like that.
So wait a second. The aerodynamics in the flight computer? How does the flight computer that goes in this fit in that?
Well, they're tiny. I mean, we got our payload section from here to here, and each flight computer is like that long.
Okay.
So we can shove things in the nose cone. We can do whatever.
You can shove things in the nose cone or do whatever. Nice. So it's actually to scale.
It is.
1/3 scale.
Yep.
All right. What's the how differently do they behave? Is it close enough that you could really learn about how this rocket's going to fly by flying that rocket?
We hope so.
We hope so. I like it.
We didn't get the chance to test fly this rocket because it's expensive and we started late. But we test flew that one, and it was great. We were a little worried that this rocket was projected to go a little too slow off the rail.
Right.
This went even slower on a scale sense, and it was perfectly fine. So we hope that translates to this one, too.
So what sort of problems might a rocket have if it's too slow off the rail?
Well, I think the main problem, especially if there's a breeze, is it goes off the rail, the wind catches the rocket, tips it over before it's going fast enough to be stable, and then it goes sideways.
It goes sideways, and then you have to go find it.
Yeah, among other problems.
Amongst other problems. So that is definitely a thing, like how quickly you get off the rail and how quickly you pick up speed and become aerodynamically stable.
Right.
It's almost like a ratio sort of thing, like the ratio of the wind to your motion. If you're going too slow, the wind is more of an effect.
Yeah, and we have rules about what level of wind we can fly at, and ESRA has rules on that as well.
Yep.
And it's, safety, even though we joke about it, very important, of course.
Yep, of course. We have a lot of fun when we do this. Like, when we joke about Fire Hazard 2 and we don't talk about Fire Hazard 1.
Nope.
Hey, it's all good. It is very important to be safe while we're out here. Anything else that we've missed? We've got the box of rocks. We've got the commercial off the shelf. Y'all are going for 10K. There's an octopus on top. Did we miss anything? I don't think so. Everybody else shrugs. Like, everybody together now shrug. Like, all right. Well, we will catch up with you when we're out there. If you see us out filming or whatever, just come up to us, tell us how it went, tell us how it's going, and good luck with your launch. Well, thank you. All right. Y'all didn't have to come very far. You came from Arizona.
Yeah, only 4 hours.
I feel like y'all had to drive like penalty miles. Like you should drive to California and then back so that you're even with the other teams.
Yeah, right. Drive all the way to Canada and back.
All the way to Canada and back. All right, folks, it's Team 95 from University of Arizona, and good luck with your launch.
Thank you.
All right. Moving right along. I'm going to pull over here for a second. Chat, how are we doing? I don't know if there's been super chats or anything like that coming in. I don't really have the bandwidth here to read them. I'm trying to interview as many of the students as I can. There's another rocket. Look, it's a rocket. But if people have been doing things like gifting memberships or whatever, thank y'all so much for the support. All right, you think we get another team here? They're being judged. There's nobody else in this aisle. Okay. Did we skip an aisle, or we went to this?
Packing down.
Everybody's packing up.
Them, but they started taking it down right.
Okay, well, let's troll around and see if we don't find another team. Again, it's coming up on 4 o'clock. 76. It looks like 76 might be gone. Y'all, I know that it is a lot of people asking me to find specific teams, but there's just no way that I'm going to find every team right now. So when we are out there, they're going to be launching the next 4 days, and I will do my best to find them when they are out there, even if I can't find them right now, okay? So I'm not trying to miss anybody. It would be so much if we were trying to run all over the facility and find each name, but thank y'all so much for hanging out with me here. Where'd Art go? Oh, there's Art. Art's talking to somebody else. Let's see if there's somebody else to talk to. Oh! They look lazy. They're all sitting down.
How's it going? Hi, YouTube.
Yes, hi, YouTube. Nice. Who am I handing this microphone to? Somebody's on the hook. Okay,
Hello.
what's your team number?
We're Team 146, Ram Rocketry from Virginia Commonwealth University from Richmond, Virginia.
Okay, Richmond, Virginia. So that is on the East Coast, and y'all drove all the way over here with the rocket?
Yep, 30 hours of driving about, so...
30 hours of driving. How many people on your team?
There's around 20, but 10 of us are here today.
10 of you are here today, okay. Have y'all ever been to Spaceport before?
This is our first Spaceport ever. We've only flown G motors in competitions before this, so this is a pretty huge step for our team. It's our third year ever of being a team, and first year at Spaceport.
So, like, all of YouTube is watching. Not really, but there's some number of people watching. What's the difference between a G motor and what you're flying here in the background?
So the letters correspond to the total impulse of a motor, so they get logarithmically bigger as you go further down the alphabet. So an A motor might be the size of a small battery, and an M motor is a $500 giant big thing that, costs $500 and weighs 14 pounds and whatnot. So they're getting bigger and bigger. So this scale of competition is something that's brand new for us. We had a lot of people build rockets of that size to practice for this. We had a lot of research and development, contacting people who've done this before, people who know a lot more about rocketry than we do, to get to this point. And so it's been a really big learning journey to kind of progress from that first initial step, getting a rocketry team founded, to building a really impressive rocket that we have today. So we're super excited to be here.
So show us the rocket here. Tell us what's going on with the rocket.
Yeah, so this is banana pudding.
It's what?
It's called banana pudding. Near our launch site in Culpeper, Virginia, there's a really good barbecue place that has a really good banana pudding. And one day we were just like, that's an appropriate name for the rocket. It's kind of our post-rocketry ritual to just get some banana pudding.
So it's inspired by the barbecue place?
Yeah, it's called the Barbecue Exchange in Gordonsville, Virginia. So if you're ever around there...
Not sponsored by them or no?
Not yet, but maybe after this,
Not yet, unless...
You're right. We have gotten the free banana pudding from them.
Is that the payload?
No, so the payload, it's actually not too far from banana pudding. So we have a gelatinous brain in there. So basically, there's a research lab at our school that does research with microconcussions. So we have a brain that's, reacts the same way to acceleration that a human brain does. And essentially, they've been doing it for, sports-related injuries, head trauma. But, a rocket puts a lot of acceleration on a person, too. So we figured that would be a good experiment to transfer over to rocketry and see if we could reduce valuable data for, purposes such as astronauts and fighter pilots and whatnot. And so we're hoping that research can go towards preventing microconcussions for people in those occupations. So that's our experiment in our payload. One funny thing is that our brain is barely stable at room temperature. It wants to melt, and we're in New Mexico, so it's not the greatest of storms. But what we have is a whole section in our payload filled with dry ice, that blue rectangle you see there, to try and keep it cool in the New Mexico heat. So we're optimistic about it. We think it'll last. But, you know, it is not the best situation for a brain that doesn't like room temperature.
I thought you were kidding at first when you said you had a gelatinous brain as your payload, but that's for real.
Yeah. It's a pretty standard rocket otherwise. It's our first competition, so we wanted to keep it simple. It's an ultimate wildman kit. We have extended the payload section to fit in that experiment. We have added some extra switch bands, bulkheads, and couplers in order to accommodate that as well. But other than that, it's a standard dual deployment. We'll have a drogue chute come out at apogee, or the highest point of the flight. We'll have a main chute come out at 1,000 feet. And other than that, we're flying with 2 MissileWorks RRC-3 altimeters. Very simple to use. We've had great success with them before. We've flown this rocket 2 times. This is the first time we're going to fly it painted, though. We flew it once unpainted, once primed, and now we get the final part of the paint cycle to fly it on. But other than that, that's about the whole summary of the rocket. Yeah.
Okay. Good deal. Do y'all feel like you're ready to fly?
I think we're ready. We're going through some last preparations. We're trying to optimize the process as much as possible. So when we get there at 5 a.m. or whatever it is tomorrow, we throw it all together, we get in line, and we're good to go.
Nice. It is 5 a.m.
Yeah.
They said the announcement.
Right.
All right. Well, good luck when you get out to the launch pad. Thank you so much for hanging out with us. If you see us out there and you have a status update, just feel free to run up to us and be like, hey,
absolutely,
we have a status update, and tell us how your flight's going or how it went or how your recovery team's going.
Yeah.
Or whatever.
Yeah.
All right, folks, this is Team 146. There you go. It's RAM Rocketry at VCU, College of Engineering.
Mm-hmm. Thank you very much.
Good deal. I'll pinky the microphone there, and thank y'all so much. All right, I'm going to step over this way because we may, folks, be out of battery. Let me refresh this. Give me just a second. Can you hold the microphone, please? Thank you. Let's flip this around like that. Up high.
And here we go. We have liftoff. Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, Atlantic. Water towers fly! Yes! Tango down to nominal. Fighting downside, FD off. Bring in, FD off. Off.